Okay, welcome everybody to our afternoon session. Our first speaker is going to be Meir Feder, and he studied at MIT under Oppenheim in signal processing, statistical signal processing, and then he went to Tel-Aviv University, where not only is he a double E professor there, but he's in a chaired position in information theory, and he is the head of the Tel-Aviv University Center for AI and Data Science. And one other thing I want to mention, I was just chatting with him a minute ago about who his mentors were, how did he get moved into this information theory area. And in his case, Jorma Rissanen had a big impact with the minimum description length ideas. And I love seeing how the kind of online or sequential version of that really overlaps the fields of information theory, computer science, statistics, and economics. So we're going to hear about that from Meir.
Okay. Thank you very much, Andrew. Everybody hears me? Okay. So indeed, as Andrew said, I'm working a lot on the interplay between information theory and statistics and signal processing in a way. This way, everything is machine learning and AI, right? What we used to call estimation is now called learning. Indeed, those ideas influenced, and I will describe those in my talk. It's strange, actually, Andrew. Our interests seem to overlap a lot, but we never had the chance to work together, although I will mention some of your work that influenced some of the things that I'll describe.
Maybe in retirement I can do more with you. Maybe in retirement.
You can come to Israel. So let me do one other thing. Speaking about these times, you know, when we have all those demonstrations on campuses, people tend to forget what happened just a few months ago in Israel. Israel was under terror attack, brutal terror attack, in Be'eri, a place which I'm very fond of. I have some people I know. A student of mine had to be locked up in a room with a 3-year-old child for 13 hours, while her father, who went out to protect her, was massacred by the Hamas terrorists. And they did it for some nature party. And, you know, they kidnapped kids. Some of them were released. They kidnapped the Bibas family. This is the mother and the 2 children that were kidnapped. One of them was 7 months old, and they are still there. We actually don't know if they are alive. So we wish that all the kidnapped people will return, and that, you know, there will be peace in the Middle East. Okay, so after this, in my talk, indeed, the main thing I want to deliver is what I call this multiple universality as an approach to tackle over-parameterized model. There is a big mystery, right? It was mentioned a little bit in other talks. How come that we have an over-parameterized model, we overfit the data, and they're still able to generalize? They're still able to learn things. This seems to be against all the common wisdom in statistics. So that will be, as I said, a major thing I would like to deliver today. But before that, I would like to give some background on the way information theory deals with estimation and statistics. And in my mind, the approach, the information theoretic approach should be adopted. It's much more clearer and cleaner than what learning theorists are using, like the PAC model and other stuff like that. And I'll try to convince you with that as well. I'll try to do this introduction as quick as I can do, so I will get to the new things. Okay, I said multiple universality, so let's start with universality. What do we mean by universality in information theory? All the information theory is based on some probabilistic assumption. We have probabilistic assumption on the channels, on the sources, and we can get coding schemes, and we can analyze what's going on, capacity, entropy, etc., under the assumption that we know the statistical behavior of the data. But in reality, of course, we don't know that. Maybe there is some statistical model that we don't know, and maybe it's even non-existent. We just have data. So the idea of universality, or the nice results in universality, is that although we build some scheme which is universal, is model independent, yet it can attain the same performance as somebody who knew the right model that fits the data, or the right statistical model of the data. So I'm working on this field for quite a few years, and as you can see, it's over 30 years journey on channel coding, on source coding with many people, and it still keep going. And I'll try to concentrate on the thing that is now of interest, on the problem of universal source coding, which is completely equivalent to the problem of online prediction with log loss. Now, I must say that before that, when I'm saying online or prediction with log loss, actually that work that initiated back in the 90s, when I did it with a colleague of mine, Neri Merchav, and when we wrote some summary paper in 98, which was 50 years to information theory, and we had to apologize. Why are we using log loss? We called it self-information loss. We tried to justify it, maybe gambling. Now everybody is using that. Now it's clear. I mean, you train a GPT over log loss with log loss error criterion. It's clear. Actually, there are good reasons for that, which I will not get too deeply into it. But remember, online prediction with log loss is completely equivalent to source coding, to lossless source coding. So let's talk a little bit about source coding. We have data, and if there exists some probability distribution for that data, we know how to encode it. The optimal way to encode it, if we ignore some integer constraint, is to allocate to the data a code length which is minus log of the probability, the self-information of the data. And indeed, if you do that, or you a little bit do the integer Huffman or arithmetic coding within 1 or 2 bits, you can get to the entropy, which is the optimal performance. And of course, the question was, what happens if you don't know the true model, or even if that model does not exist? So the way to think about it is that no matter what you do when you encode the data, or when you predict the data with log loss, you essentially assume some probability on the data. It might not be the true probability, but there is an assumption. Let's call that coding probability Q. And the relation between the coding probability and the code length is simple. It's just if you allocate a code length of L, is equivalent to say that you allocate a probability of 2 to the minus L. They're completely equivalent. And what happens if you use this Q, which is different from the true probability? You pay a price. You pay a redundancy, extra price, which is the divergence between, the information divergence between P and Q. Now, of course, the question is, okay, we are convinced that coding is like just assigning probability to the data. How to choose the right assignment probability? How to choose this Q? Oh, here are 2 quick slides that I mentioned already on the equivalence between coding and prediction with log loss. Let me just skip them. You can see immediately how they are related. So coding and prediction with log loss are the same. And as I said, everybody is now using log loss without apologizing, not like it used to be 30 years ago. As I said, the GPT are doing that. So let's get to our problem. How do we choose the right coding probability that we want to assign to the data? Q. So I will answer this question in several levels. The simplest answer would be under the following assumption. We say we don't know the true probability, or what probability fits the data, but we assume that we have some class of probability, some hypothesis class, as the learning people like to say. Well, it's a weaker assumption that we know the probability, but it's still an assumption. You can say I'm not so satisfied with that, especially when today our models are so large. But I'll quickly describe what happened, what is universality with respect to a given model class. But as I said, that's not what we want to solve. The situation is that we have maybe very large model class, or we don't know the model class. So I'll extend that with the older idea. Andrew mentioned Jorma Rissanen, like the MDL kind of idea of how to deal with large class of models somehow. And then I'll try to concentrate on the proposal I'm saying, how to deal with large model, which I would call twice, multiple, or hierarchical universality. Okay, so as I said, we don't know the true probability, but we assume that we have a class of probabilities. And then the question is, what do we say about the data? Here also we can have a few levels. The simplest assumption, which statisticians usually like, is to say there is some unknown parametric model. The true data come from one of those models. So that I will call the stochastic setting. We don't know the true probability, but we know the class from which that true probability of data came from. That will be the simplest one. A more elaborate assumption would be, we have a class of probability distribution which is used for some kind of a reference, but the true data comes from maybe another larger probability with some probability distribution which may be outside this class. Okay, let's call it the misspecified setting. And here I'll mention some work that you did back in the 90s as well, Andrew. Still, the really interesting assumption, or no assumption, is to say I have a class of probability model, but I don't assume anything on the data. The data is what I have. That's it. Any assumption that I can make in the data is some wishful thinking, right? And we call that the individual setting. We just have the data. So under those three kind of assumption on the data, we know how to solve, or at least in information theory, we can give very precise criteria, not just hand waving, ERM, etc. That's what we want to achieve. In the stochastic setting, we look at the regret, which is this divergence that I mentioned before. It depends on the true probability and on the assigned probability. And we ask what would be the assigned probability, to minimize Q for the worst case of theta in that class. So we have a min-max problem that can be solved. In the misspecified setting, we have also a min-max problem, which is a little bit more elaborate, because now we compare ourselves not to the true probability, but to the projection of the true probability over the class. And in the individual setting, again, we have a min-max problem. But now we compare, there is no true probability. We just compare to the best fit of one of our models in the class to the given data. And we do, again, a min-max problem. Interestingly, all those problems can be solved explicitly. So the simplest problem is the stochastic setting. It's called the redundancy capacity theorem. Again, well, I have to mention yet another inspiration. I went to MIT. I took the information theory class by Gallagher. And I almost regretted that I did signal processing at that time. And I wanted to move. By the way, here is another story. Gallagher told me at that time, forget it, information theory is dead. you are in a great place in signal processing. But anyway, one of the things I learned in his class is this redundancy capacity theorem. You can relate the redundancy, the min-max redundancy of universal coding to sort of the capacity of this a class of sources, the capacity between the index of the class to the observation. And so we have a nice information theoretic expression for how much we pay for not knowing the right model in the class. And if this capacity is small, then we are indeed universal. We are universal. We achieved as if we knew the right model. And we have an explicit solution for that. In the misspecified setting, it's a little bit more complicated. As I mentioned, Andrew, there is a paper, I hope you remember that, from 98, that you call that relative redundancy, that paper. But again, it can be solved. That paper, it was mentioned, and it turned out that not too many people worked on that in the information theoretic way, although it's sort of learning. And recently, with Polyansky and another student of mine, Amichai Pensky, we sort of completed that min-max solution. And the individual case is also, it was solved in '87 by Shtarkov, and it's called the normalized maximum likelihood. Again, it's the exact min-max solution for the individual setting. So to summarize what I just said, if we don't know the true probability or the best probability in the class, no matter under what assumption, we know how to solve it. And it's not a big deal. It depends on, as you can see here, it depends on the complexity of the hypothesis class. In the individual case, we call it gamma. In the misspecified case, we call it F. In the stochastic case, we call it C. And if all those terms, gamma, F, or C, are small, what do I mean small? That they are sublinear in the amount of data, we are universal. We are happy. And, that's another thing that related to the work of Andrew and Clark. In many cases, that capacity, and not only the solution, well, I didn't mention that the solution in the stochastic case and in the misspecified case are just Bayesian mixture of the data. And the question is, of course, how you take the weight of this Bayesian mixture. And there are ways to evaluate, at least if it's nice parametric family, under some constraint of the achievement of a Fisher information, you can get explicit expression for the capacity or for gamma, and also for this is just by a nice analysis of Bayesian posterior in certain cases, as I said, the well-known paper by Barron and Clark. And again, so it shows us that although there is difference, no matter what is our assumption on the data, if we are dealing with a class which is not too rich, its capacity or its F or its gamma is not too high, we are universal, we don't have any problem. And it fits, of course, the classical statistical assumption, trade-off between bias and variance. If you take a large class, you reduce the bias, but you have large variance, and so on. So it really relates to all the classical statistical knowledge that we have. And here is yet another observation. When you do this Bayesian thing, one other thing you can think about that is that you give an exponentially higher weight to those parameters that fits the data more. So the higher this probability, and probabilities for a sequence are going exponentially, the higher those probabilities are, they give more weight in the posterior, and actually tells you that the choice of the prior, of that W, I mean, it's important, but it's not too important. And that, of course, explain why techniques like ERM or maximum likelihood work. Because maximum likelihood just maybe approximate this integral by the maximum. And you can live, but that's not the really right thing to do. Okay. And, well, here is some quick variation that I hope I will have time to say. So far I spoke about online learning, assigning probability to the entire data. But in learning, people like to have what we call batch learning. We have training and test. That's the way it's usually posed. So you can formulate that situation as well. Again, in information theory, we didn't deal with it so much until recently. I mean, there were some people that talked about it. I can mention some work that I did back in 2018. But anyway, even in this batch case, we can look on a min-max problem. That's for the stochastic case, and we have it for the misspecified case or for an individual case, which is more tricky, but I will not get into that. And for all of this, there is a solution. At least in the stochastic case, what's nice about it, again, you do some Bayesian thing, but the prior have to maximize a conditional mutual information, not the joint mutual information for the entire data, because you are in that situation of training and test. So you get some interesting solution. Maybe I'll just mention it quickly. When you get to this basic problem of predicting the next bit under Bernoulli models, we know that Jensen, I only 5 minutes, so I'll skip it. Anyway, you are far away from the Jensen kind of prior. You're far away from the add beta half problem. You get another interesting solution with a strange beta, but I will not get to that. Let's go to large class of models. The situation is, as I said, we exchange the assumption of not knowing the probability by the assumption that it could be in some class. But how we choose the class? We don't know how to choose the class. So let's have a big class. And that's the situation now, like neural networks. Trillion parameters, 500 billion parameters, who knows? definitely not enough data to estimate those parameters. What do? We may think about the large class as a union of smaller classes. One example is what, again, another inspiration, Jacob Ziv, they did with finite state models. So you can think it's a union of finite state models with larger and larger number of states, and that actually led to what they call finite state complexity, some extension of Kolmogorov complexity. But their approach, and in a way, Rissanen's approach, in my mind, was missing something. The way they, like Lempel-Ziv algorithm, become universal and deal with any ergodic source is by just increasing the model complexity as you have more data. That's not, you can say, okay, great. If I haven't, so I don't, the way it was done practically is by increasing the dictionary size as you have more and more data. So essentially, the way to deal with complex model is you wait until you have enough data to deal with more and more complex model. But that's not what is done today, right? So this is why we go to twice universality. And again, we are in that situation. We have a huge class of models, which is composed of smaller classes of models. You can think about that. Each of them has its own capacity, its own gamma or whatever. Each class has its own universal probability. And now we want to do another universality, being universal with respect to those representative of each class, and do another layer of universality because you don't want to consider the union of all those classes, like the Lempel-Ziv. So actually, this idea was turned originally by Ryabko in '85, but he did it in a very restricted way, and he called it twice universality, and now I'm generalizing to multiple universality. And so here it is. Each Qi is the universal probability of each class. You try to do min-max. You try to find a single Q that can represent all the representatives and do it as many times as you want. Indeed, one problem is when you look at that min-max, that class of representative of each class can by itself be very large. So you would pay another universality cost, which is too much. So this is so there are two ways to deal with it. One way is to go to multiplicative redundancy, and I'll quit that. The more nicer way is to do another layer of universality. So you arrange those classes by hierarchy of classes. Each one of them, the size of the hierarchy is never too large, so you will not pay more than what you would have paid if you know which class the model belonged to. And you can do it as many times as you want, depending on the complexity of the model that you are dealing with. And a canonical example, simple canonical example, is universal representation of the integer. You can say, what's the big deal with this problem? When you look at all the integers, and my model is that if I have 7, I have with probability 1/7. Now I have infinite number of models. If I want to be universal with respect to all the integers, it's a 2B class. So you have to arrange them in some way. A natural way to arrange those classes is by the number of bits that you allocate to each integer. And this is how it is described here. And when you do that, and you do it in several universality layers, you end up with the famous Elias code for the universal representation of the integer. And this canonical example gives you a hint of how to deal with more and more complex models. Let me indeed skip because I'm running out of time, so you can do it in several hierarchies, and you get, and of course, the code itself is easy to explain. In order to describe an integer, I take its binary expansion, and then I put a header of how many bits I use for the binary extension, and then I have a header of how many bits I use for describing the header of this binary expansion, and so on, as much as I want. At the end, I just do maybe the multiplicative description one time. In Markov model, it's easy. That's related to the MDL. Now the hierarchy is model order of higher and higher degrees. And you can do the same trick, and you can be this two-part code that was suggested by Rissanen in many cases. The point is, when I try to explain to the computer scientist what we essentially did, we replaced the strong request for uniform convergence with non-uniform convergence, depending on the data. Sometimes I'm adapting to a specific data larger model, and then I converge slower. And sometimes I'm satisfied with a simpler model and I converge faster. Who says that for the huge trillion parameter class of models, I have to do uniform convergence? I can do it in several layers. And yet another example, well, a really great example is the context-free weighting algorithm that essentially doing the same by going over all the three models of memory, which is a much more elegant thing that what I did with a single paper. Actually, I have two papers with Yor Marisanen, but that paper was just before the context-free weighting, but they did it much more elegantly. We just did it relatively brute force. So I think I borrowed it from Yanis, your slide somewhere. This is the three models, and one way to describe this, this is the context-free weighting. This is the redundancy to pay, but here is, I want you to have this slide. The way to think about the context-free weighting algorithm is the following. Think about, we said that prediction and coding are the same, so think about coding. So multiple part, 1 minute, I'm sorry. Multiple part coding would be to first I have to tell you how many leaves I have in the tree. That's an integer. That requires not so much. Then I have to tell you, suppose you know now how many leaves I have, which tree I choose. It turns out that the number of binary tree, at least, with S leaves goes like 4 to the S. It's the Catalan number. The log of it is proportional to S, but not to N, which is great. And then you describe the parameters and the entropy, and it works for any memory size. And I'll finish with the more interesting thing that we are waiting for. What do you do with neural networks? Well, one thing you can do is with perceptron. Perceptron, you can do this multiple universality with respect to the margin. If your data give you a large margin, you know that we can project the data into a smaller dimension. And so the universality layers is about the dimension of the data. It can also be there could be another way to do it, and that's with general linear models. Again, you can look at the sparsity. How many parameters of the linear models are active? When you remember the relations between coding and prediction, you just have to think about coding. So again, I have to tell you how many are active, which of them are active, and then the parameters of the active ones. And again, the redundancy, the extra cost, is proportional to K, to the number of active components, and not the size of the data. And this is an experiment with this. It works pretty nicely for linear regression. And what about deep neural network? And that will be my maybe sparsity, but that will be my, oh, I missed one slide. Here it is, okay. So you can do the same trick of sparsity for deep neural network, and here is my conjecture. A huge, large neural network is composed of smaller networks. You can describe the smaller networks by the number of nodes that are active. And then you can organize it this way. And how much do you pay? You have to tell in each layer how many nodes are active, and then which are active, and what are the parameters. And you end up paying the complexity of the smaller network, not of the big network. And why stochastic gradient and ERM works, for the smaller models, you have a lot of don't care about the parameters. And all those don't care actually give you any iterative algorithm will converge to the larger space of don't cares, and then you get essentially this hierarchy of model for deep neural network. As I said, there is another elephant, what is the hierarchy? But that's another philosophical question about Kolmogorov complexity. So thank you very much, and sorry that I took 2 more minutes.
Thank you very much. A question?
Yeah. I'm not sure, but isn't it what you are describing similar to adaptivity in statistics?
I'm not sure I know what is adaptivity in statistics.
Adaptivity is when you have a nested class of models, and even often it's a nested class of distribution, Andrew can explain.
Okay.
Yes.
Well, one thing-
Can I go ahead and answer the question? It's very related. It's very related. This is another example of how interesting results are developed in both communities that can be very much related to each other. So that's a good connection.
And yet another comment, I didn't assume that they should be nested. They are not necessarily nested. That's the language that you are talking with. It could be nested like Markovian models, but in the tree models, they are not nested. Different trees are not nested within each other. So that's a more general way. Even the smaller networks are not necessarily nested within each other, right? Okay. So, okay.
Peter, you have a short one?
Yeah, so you often Elias coding is only done in kind of two steps.
It could be done in 2 steps, and then you get the first Elias code, but you can do it many steps.
So when you say multiple instead of twice, is that
You keep exactly. You do the how it's called the gamma coding or whatever, the delta code, they do multiple universality. Multiple universality is a better idea because if you see that the number of classes is also large, arrange a hierarchy in that. And then you can do it as much as you can depending on your language. And that's, I believe, what's going on in large models.
Good. Thank you very much.
Thank you.
Let's thank him one more time.